Hello community, so great that you are back. Yes, today we look at a real-world implementation of multi-AI agent system at Los Alamos National Laboratory. A real-world use case. And Los Alamos, they work now or they cooperate now with OpenAI to advance your national security applications here. And they have supercomputer. Absolutely, they work here on understanding here the latest secrets on quantum computing here. Just a publication from a month ago. So absolutely beautiful. And they now published here how we use AI agents. And they say, hey, we represent here the URSA agentic workflow for accelerating scientific efforts here at Los Alamos National Laboratory. And this is for use by the scientific community. And we show you a set of modular composable agents coupled with tool use beautifully. And all the assistant can do now is to hypothesize, plan, execute research tasks to supplement here domain expert in accelerating the research outcome. So agents for acceleration in science for accelerating the research outcome. Sounds great. Is it great? So URSA uses here agents dedicated planning, hypothesizing, researching and executing computational tasks, plus they have here the integration to real experimental machines. They work here, the use case, of course, here in inertial confinement fusion, especially trusted radiation hydrodynamics model here for ICF. So our laser fusion application, and it's great to have an inside look now. How do they use here AI? Now, this topic here is now from here, publication August 2019. I cannot show you the original publication. I would have to pay quite a lot of money since it's from 2019. This is not anymore here an open source. This is here already on dedicated servers here. So this is it, making inertial confinement fusion models more predictive with application of machine learning. Great. So you see for 6 years they are researching this. But of course, here how you can combine now expensive experimental model data with large-scale physics simulation to the real-world experiments and the digital twin right next to it, done by AI. And now AI combines or controls the experiment and the digital twin. So this is now really the next step. But you see, they are already 6 years into this. And of course, they are not alone. They are working here with Lawrence Livermore National Laboratory on this topic with their supercomputer. So great. So what we are talking today is, yes, finally, AI for physics. But let's be a little bit more precise since we're here in science. Now, it is large-scale experimental physics. So we're trying to optimize here the research process done by AI for the real experiment that we do with huge machinery, and AI controls the machinery and the digital twin for prediction how to optimize machinery in the next run. So we do have a direct real-world feedback for AI experimentation. Now you might say, hey, is this a good idea with fusion experiment when you have shown us that in one of your last videos with science AI and it was not really working out so great, This was a work by Carnegie Mellon University. And remember here the co-scientist AI by Google and Stanford, well, it had maybe some limitation. Or just look here at Sakana AI. No, this is from August 24. My goodness, already a year ago, no? So, yeah. Okay, let's have a look. This is the paper of today. By end of June 2025 from Los Alamos National Laboratory. Thanks to all the authors. Beautiful. They show us how they use AI multi-agent system for AI, for research, for real fusion research done by AI. And they tell us, hey, we chart a path toward AI system that actively do science. This is something that is fascinating, but it's something a little bit that's, I don't know, I'm a little bit worried that AI is doing science on a fusion model with real world fusion, laser fusion. Okay, so they say, okay, we chart a path to AI system that do science while illuminating the gaps here that remain in the autonomous use of agents for critical science application. So they tell us, great, but there are also some gaps. you do not want to have in laser fusion, no, if you have an autonomous use of AI agents for safety critical science applications. But to be clear, it is not about writing code. It is already the next step. It is about automating the scientific method itself. Experiment, discover, reason about the results, have a new hypothesis, have a new idea, formulate it, build a new experiment with new parameter, with new hyperparameter, run a digital twin, simulate this new idea, and if the simulation works out, go to the big machine and run the laser fusion experiment in real time. And then the loop starts all over again. So I think a beautiful experiment here, end of June 2025. URSA, yeah, please, there are so many URSAs. This here is a paper of another URSA, but this is another URSA. So I don't know why people love the term URSA, but our URSA is this one here, Universal Research and Scientific Agent, and not any other URSA. Great. Now let's have a look at Los Alamos. And they say, listen, we have here a modular concept of agents, and I'm going to introduce you here. And this is here the original screenshots copied here from their publication. And you see here in quotation mark, it is really their formulation, because there's something I have to tell you. They use LangChain and LangGraph for this. Now, I personally stopped to use LangChain and LangGraph a long time ago. I'm not an expert in this, and I have a certain emotion to this, especially if it's about a long time ago, if you wanted to have a debugging experience and a debugging excellence. But never mind, let's have a look at this, the planning agent. In terms of a LangGraph network, they tell us here the agent consists of 3 nodes, a plan generator, a reviewer, and a formalizer that each use here a backend LLM. You see, we have here the imprint of the LangGraph structure already here on our new methodology, how we use AI agents. Maybe this is the part that I do not really feel comfortable with, because I want to be free in my source and I want to build something absolutely creative and not say, I use now LangChain or LangGraph or whatever will come next, and I'm limited by the structural ideas and the structural implementation of those systems. But hey, you have to do it anyway, so let's go. Then we have the execution agent. Yeah? This is the nice thing that goes here now with calling Python function as tools. You have a Python wrapper, must be used for adding additional tools. Remember, you have a supercomputer just standing right next hallway, so absolutely use this here for the digital twin calculations. Multiple tools, at least 2, a tool that writes files here to a workspace and a tool to execute here system commands here for the real machinery. Then they say we have a research agent. And they're so cute to say, yeah, utilize web search through DuckDuckGo and scraps here the web content to collect and summarize information for solving here a given problem. No? And also, again, here consists of a generation phase, a review phase, and a summarization phase. You know how much can go wrong just at these 3 phases. And then this is the interesting part, I think, the hypothesizer agent. No? This is here, the goal here of the hypothesizer agent is to utilize the web search and then have a beautiful debate to hypothesize possible solution to a given user prompt. So the difference they tell us here between the hypothesizer agent and the planning or the research agent are in the internal iteration for solving the problem and the structure of the output. And again, the hypothesizer, you see the imprint here of our software implementation. 3 internal sub-agents, the hypothesizer generator, the critic, and the competitor. Okay, but let's go with this. And then, of course, we want to have access to the scientific literature, so we have an archive agent. Yes, you get it. Now, let's have a look at real-world example, because this is exactly why we're here from Los Alamos. And they tell us, just for the data preparation step, this is the task they give here to their AI system. Say, hey, look for a file called, whatever, CSV file in your workspace, and then execute a Python file to load the data into Python, split the data into training and test data sets, visualize the training data for a particular whatever, fit a Gaussian process, fit a different neural network, access the quality of fits, access the uncertainty quantification of the two models, standard data preparation. And the system, the way it does it, the way how to describe it is great. So they have a planning agent that generates now a step-by-step plan to solve the problem. And now it's interesting how they decouple the complexity. No? They say now each of those steps that was generated by the planning agent is now passed to another planning agent tasked with breaking down their own particular step into multiple sub-steps to handle the fine-grained details. So you see what's happening. We break down complexity, break down more complexity, and then each of those sub-steps was passed sequentially to an execution agent to carry out the execution. And in reality, it has 7 phases: environmental setup and validating the existence of the data pre-processing, the fitting here of the Gaussian process, the fitting here of the Bayesian neural network, assessing your predictive capability, assessment of uncertainty quantification, and summarization and presentation of the results. A rather boring, rather classical, But let's have a look at this. This is now an experiment. This is now a real-time experiment I love. Yeah? You say, listen, there was a new paper published somewhere in the world, great, about a double shell inertial confinement fusion design and the relevant physics to consider. So here we have a new idea in theoretical physics that we can implement on our machinery in our experiment. And they say that work was done for whatever, and now we need a new design to run our machinery on this new design in our laser facility using here, I don't know, specific laser configurations. And your goal, AI, is plan the target geometry for a new experiment with 5 layers, evaluate the proposed design with the Helios radiation hydrodynamics model here in our supercomputer to get here a simulated neutron yield and integrate here this with our dynamics. And now, Helios, if you're not familiar, is a 20 terawatt CO2 laser fusion facility. I think it's operational quite a long time, somewhere in 1978, somewhere I've read. And so you see, it's great. They have a new research paper somewhere in the world. They say, hey, we have a new idea. And they say, hey, we have the machinery. So let's look at the paper. Let's understand the paper. Let's analyze each of the conditions of this new research paper. Let's see if we can script this into our real-world experiment configuration. Can we map this to the real world? And then we just run it. And then we see if we really get the result that was proposed in the theoretical paper. This is it. They use here for the hypothesizer agent, they use a O3 mini model. Oh, poor. But now they're operating with OpenAI, so maybe they can afford now the real O3. And at least they used the O1, a really old O1, for the executor logic. Okay. Now, let me tell you that I love the idea. It is beautiful. This is really, we need AI that has interacts now with real world, with the external world to get feedback, to learn, to develop memory, to better. We have autonomous systems, self-learning system. Absolutely love the idea. But I noticed here the way you implement this, and at first I didn't notice why I was somehow irritated by their formulations. If you implement it in a particular given framework, and let's say this is here with LangChain and LangGraph, that maybe you would feel is not the leading and bleeding edge of research, there is something that I feel we could go a step further. But now you know it. Maybe this helps you. It helped me to understand here the code block 1 from the planning agent. Looking at the code, I got a little bit more deeper understanding what they're actually doing, especially here with the execution agent. If you have then here the tool used that is available, now of course, particular to their supercomputer, particular to their experimental designs that they have built in their labs. Great. And then we have the OHAV agent. Yes, you get it. GPT-4 vision preview. Okay. And the hypothesizer, where we have a hypothesis, a critique model, a competitor model, and a conversation model. Great to combine this with web search. Okay, so it depends a lot of the internal reasoning capabilities of O3 mini. I mean, go with O4 mini high at least, but okay, O3 mini. And the research agent is a little bit disappointing if you have a look what they are just combining here on a linguistic level and not Nothing else more. Okay. Now, prompt structure. I was really interested in their prompt, and they are beautiful, transparent. Yeah? And they say, give you a different example. The planner execution, simplest case, no? The planner prompt. You've been given a problem and must formulate a step-by-step plan to solve it. Consider the complexity of the task, beautiful, and assign an appropriate number of steps. This is now really dependent here on the complexity capabilities of your AI system. No? For each step, specify the name, description, generating or executing code. Do we need access to a tool? Execute or expected output of the step, how to evaluate this. Consider a diverse range of appropriate steps, such as data gathering, data pre-processing, analysis, modeling, hypothesizing, testing, visualization, evaluation, and validation. Execute a prompt, yes, and a reflection prompt. For clarity, completeness, relevance, feasibility, and efficiency, you have here all the text. And then you have, if everything passes, you get an approved. Great. Now it gets much more interesting if we have research, hypothesis, and archive. Yeah? Now the research prompt is interesting. Yeah? They tell the AI, hey, you are an experienced researcher tasked with finding accurate, credible, and relevant information online to address the user request. Before starting your search, so I guess this is somehow connected here to a graph RAG or whatever RAG system they have, a reasoning RAG, multi-agent reasoning RAG, and ensure that you clearly understand the request. This is absolutely important. Yeah? And then they say perform the following actions. And now we have a template. And that template is positive and negative. It is great that you have reproducible steps that the agents should perform. But otherwise it is also limiting because you squeeze here the intelligence into a pattern. But it's nice because the first step is here formulate one or more specific search queries. Review now the multiple search results you get back. Evaluate the quality, the reliability, and the recency of each data source that you used. Very simple problem for any RAG system. Summarize the findings clearly and concisely, and no problem for any RAG system. If inconsistency or conflicting information arise, clearly communicate this to the human user, explaining any potential reasons or context behind them. Continue performing additional searches until you are confident. So until our O3 mini model is confident that it can solve now the laser fusion, let's say, experiment with a complete new hyperparameter set. Provide a final summary, great. Critique, of course, you critique the correctness, the completeness, and provide a structured evaluation on identify here the level of strictness that is required. No problem for autoregressive next token prediction system. No, the level of strictness in laser fusion. Clearly list any unsupported assumption. No problem for an O3 mini model. Identify any missing information. Yeah, I think you get the idea, no? Hypothesis. Here I show you agent 1, 2, and 3. So we have a generator prompt, we have a critique prompt, and we have a competitor prompt. Yes, you have an interplay, but since it's all the same LLM, I mean, yeah, what do you expect that you get? And archive, yeah, you have with and without images. Great, you go with GPT-4 Vision. Okay. Great. Now let's come to the final insight. And here a quotation by the authors. And they say they're operating with LangChain and LangGraph, and they say, and they address hallucinations. And from my time with LangGraph, I understand that debugging was not the easiest case, or I was not intelligent enough for this, sorry. But they say, while hallucinations are a problem in all human LLM interaction, in long, complex workflows, hallucination can be hard to detect, and they talk about here Los Alamos experiment, and those hallucinations invalidate all downstream results. Well, guess yes. If you start up a multi-million-dollar laser facility with some incorrect hallucinations by an OpenAI model, this could be an interesting experiment. No? And they say, it is so important for generated code results and data that they are reproducible by a human. Absolutely. No? If you don't understand how the reasoning is within an AI system, if you do not understand here the step-by-step logic in the causal reasoning chain of thoughts, if you want, yeah, you will not start up a multi-million-dollar machine, no? You never know what's gonna happen. But here at the end of my video, always give here the time to the authors here of this study. And it's interesting. Have a look at this. This is really here the last paragraph, and they say, hey, though scientific agents like URSA are only beginning to emerge, the workflow they enable, synthesizing broad research information and autonomously, relentlessly testing and iterating on novel concept with advanced reasoning, it sounds so beautiful, no? They promise to drastically accelerate scientific discovery. And this is beautiful. This is the main topic of AI if you're a theoretical physicist, no? But they say this process carries the potential for a significant positive technological and societal, okay, if you have endless energy, transformation, for better or for worse. The powerful capability is inherently dual use, presenting substantial safety and security risks. And this is interesting. If Los Alamos suddenly talks about safety and security risk, they say absent robust oversight and guardrails, these systems could be exploited to design new destructive technology or assist in illegal activities. That's a strange sentence, no? At the end of a research paper. Moreover, the authors tell us their development introduces a classic game theoretical dilemma. Pursuing agentic AI carries security risks, but the failure to do so risks falling significantly behind technologically in a potential arms race. So what does it mean? Should we just race along just to not theoretically fall technologically behind anybody else? Is this worth taking here, these security risks? Why are they addressing the security risk here so massively in a publication by Los Alamos National Laboratory on AI? Interesting. If you have thoughts about this, the comments are open. Now, the positive side of this paper is they really try here to tackle here the core creative and the analytical task of a typical human researcher. No? If you work there, I've worked there, not in this department, but in general in science, no? It's a hard life. Hypothesizing, planning, experimenting with huge machinery. You work days and weeks just to set up the experiment. You run it maybe in 5 seconds, everything is done. Then you go, you have to understand here the data that you generated. You learn from your mistakes. You have a further iteration. And it is a long, boring concept here, scientific discovery. Now, if you could use AI to accelerate those processes, great, beautiful, amazing. But especially if they talk here about AI carries here the risk and they talk security risk here in fusion, maybe be a little bit more careful in the way you implement agents and be aware of security risk that you might encounter. If you kind of enjoyed this video format here, why not subscribe? And I see you in my next one.